1, 2, 3. Test, test, 1, 2, 3. Okay, this is EasyEDA live stream for OpenSTM. Testing 1, 2, 3, 1, 2, 3.
蛮清楚的，蛮清楚的。
我做着。
Hi everyone, and welcome to EasyEDA live stream. I'm Mao Weiling and I'm from HQST.
Hi everyone, and welcome to
EasyEDA
in
live stream.
I'm Mao Weiling,
I am the author of HOPG, and maybe you have heard about it before, or maybe not. Never mind, I will introduce the author my project in this live stream. You have heard about it before, or maybe not. Never mind, I will introduce the author my project in this live stream. You have heard about it before, or maybe not. Never mind, I will introduce the author my project in this.
Today we invite a very familiar friend. 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 Today we invite a very familiar friend.
Testing.
还有你可能要做直线，你有点就是这样。
啊，
对，这样做。
椅子可以抬高的吗？还可以高吗？
可以的。
对，姿态对的，对的，抬最高，练习一下。
Sorry for the interruption, and now everything may be okay. So, Selena, you can make an introduce for yourself.
Okay, I'm Selena, a hardware engineer here at EasyEDA. Today, I invite a very familiar friend, William Ma. He holds a PhD from the Hong Kong University of Science and Technology, and he's also a senior engineer here at EasyEDA. Some of you may remember his last visit. He brought us two amazing projects, a keyboard and a USB expansion dock. And today, he's back with something even more impressive. It's called OpenSTM, a DIY scanning tunneling microscope capable of building an atomic level STM from scratch and successfully scanning the carbon atom of HOPG. How cool is that? So let's give a warm welcome to William.
Yeah, thank you. And maybe you have heard my project before, maybe not. So never mind, I will give you an introduction and technology details about my project. So let me switch the screen to introduction here, and this is about my project. So let me website of open source hardware lab, and my project is currently available on this website. A website of open source like search OpenSTM available on this website. A website of open source like search. Wait a second, and this is my project website. A website of open source like search. Okay, and the voice may encounter some issues, and now maybe okay. So let's continue. And this is my project, and click it. You can get into the home page, and there are many introduction of my project. And here we go. This is the HOPG. Or we can say the graphite image obtained by my microscope, and this is my microscopy. Yeah, this is, and as we can see, every spot here, we can recognize them as atoms. So the distance between each atoms we might regard as 1 or 2 angstrom, in which 1 angstrom is about 0.1 nanometers. Well, so this this is so-called scanning tunneling microscope. So this is my YouTube channel, and you can search Links Mary, and you can get into my YouTube channel. And this video illustrates all the details about my scanning tunneling microscope. So basically, we can, if you don't know what the scanning tunneling microscope is, I can give you a brief introduction. So maybe we can. Yeah, we can get to the Wikipedia, and we can see all the detailed information. So in short, before the scanning tunneling microscope was invented, we cannot obtain the atomic level image of any material. Since Heinz Roher and Grant Binnig in IBM, since then, and they invented the scanning tunneling microscope, and in which it is a Nobel Prize project. So after the invention of scanning tunneling, of STM for short, now we can observe the atoms with the image. And my project is followed by John Alexander and Dan Broad, which is two pioneer of DIY STM, and I follow them and build my own one. And this is my project. So how a STM works? So imagine that we have a tip, and so-called a tip. It can be PT, or it can be any other metal material, and we make it very sharp. And we got a sample. It can be a graphite, and then we can apply a very little voltage between them. And in my scenario, I will apply like we might apply like a 10 or 12 millivolts. And if we move the tip, the current will be proportional to the distance. And if the distance between tip and sample is closer, the current will be greater. And if they are far away, the current will be smaller. So after the scanning, we can observe the shape of the atoms with the current. So this is the working principle of my project. And yeah, all the PCBs of this project is accomplished with the EasyEDA, and we can see all the boards here. It's using EasyEDA to draw the PCB. If you are interested, I can show you my. And this work is published on HardwareX, and if you want to replicate my project, and with the noting that it is not easy thing to observe the atom, so you may encounter many difficulties, but feel free to email me. And this paper on HardwareX concludes every details of my project, and the cost and only material of my OpenSTM is $300 or 2,000 CN Chinese yuan. Yeah, I can give you a brief introduction. So my project, like introduced a few minutes before, we got a scanner and we got a sample here. And because the tunneling current is very, very small, so we need a preamplifier. In this case is a simple TIA amplifier. and we have to make a coarse approach mechanism, and because the tunneling distance, in our case, the distance between tip and sample is around 1 nanometers, and obviously our scanner cannot move in millimeter range, and we cannot bring the scanner and sample together very close just with our hand. So we need a coarse approach mechanism to bring the tip and sample into the scanner's range, and we got a control circuit, which is in my. Okay, there encounter some questions. Sorry for the interruption, and so let's continue. So now the screen, so the image looks better, and yeah. So to DIY such a STM, we have some difficulties have to overcome. We have to overcome. The first question is how to make the scanner in such a very high resolution. So when the atoms is very close, and the scale of the atoms distance is between is like picometers or nanometers. So we need the tip move with a very, very high resolution. So the first difficulties we encounter is to make a high precision scanner, and the second difficulties is to how can we implement the coarse approach mechanism, and the third difficulties is to make a very sensitive current amplifier, and the rest of the difficulties is to make a control circuit and our software. So let's solving this problem one by one. So we can back to one of the most famous DIY STM project, Dan Broad. Okay, and if you are interested in the DIY STM, you definitely heard this project before. Yeah. So Dan Broad, he he DIYed his own STM and scanned with his STM. He got a very beautiful image, and yeah, this is STM. So learn from him, and in his website we can see how he made the scan head. And basically, the piezo buzzer is his scan head. And this scan head is so-called and this scan head is actually from another person who is called John Alex. John Alexander. Maybe there's no his profile, and we can see his profile here. We can scroll down. Here. Yeah, John Alex, and we can visit his website. And he is really a pioneer for DIY STM, and we can see that his project detail. And he invented the disk scanner, and which like compress our cost a lot. And so in scientific, in official, like a very standard STM, we will use the scanning tube to accomplish the tip movement. And for a commercial scanning tube, it will cost 5,000 CNY to buy one. However, for the disk scanner, the core of the disk scanner is the piezo buzzer, which only costs few 2 or 3 CNY. So it really compressed the whole cost of STM. And the working principle we can look in here, and it is basically the buzzer, the piezo buzzer, is consists of 3 parts, like the stainless steel, the bottom, and in the middle is the piezoelectric ceramic, and the top is a silver electrode. So when we for the piezo material, when we apply a voltage between the top, and this in this case is a silver, and the bottom, the stainless steel, the buzzer will bend up or bend down like this shape. The genius point is then cut the silver electrode into 4 parts, 1, 2, 3, 4. And if the silver layer is working like in a whole part, we apply a voltage to all of these 4 areas. The piezo buzzer will only go up and down. If in this scenario, if we attach a tip to the buzzer, the tip will only accomplish a z-axis movement. However, if we cut electrode into 4 parts and apply a different voltage between the positive X and negative X, and then we attach tip to it, the tip will bend, will be taken into an X and Y axis movement like this. And likewise in Y axis, we can apply different voltage on Y area, and the buzzer will bring the tip moving to move back and forth in Y axis. So this is the most genius point of this disk scanner, which compress a lot of cost, so make the DIY STM feasible. So the first, we solve the first difficulties, the scanner, and because of the properties of the piezoelectric material, when we apply few volts voltage, the buzzer will bend in nanometer scale, so it can move with a really high resolution. So this is the first difficulties we have solved. The second question is how to bring the tip and sample into the range of into nanometers range. So so Dance, this is how Dance solved this problem, and he used like a lift and a mechanical lift, and we can see maybe. Let me find an explanation. Maybe it's here. No. So let's just take a look at this picture, and we can see that this is his scanner, which will mount a tip on the top to it, and the bottom of it is the sample. So he placed 3 screws here. When you like spin these screws, the scanner will move up and down. So that's it. That's very simple. You using the fine screw, and you can accomplish the movement. And obviously, it's very difficult, and you have to spend a lot of patience to fine tune, right? So after that, he placed a motor, a stepper motor here to control the screw. However, in my first and second generation DRSTM, I use his structure. However, I find some problems with this structure, and the question is, if you use your hand to spin the screw, you have spent a lot of time to fine adjust. However, if you use a stepper motor, and the stepper motor will generate a lot of heat, and because every material, the expansion coefficients of every material is different. When a temperature change, with a very tiny temperature change, and they will cause so-called the expansion coefficients mismatch. So the tip and sample distance will change significantly. So this is the question. This is the difficulty I encountered. And in first time, so in the very beginning, I was struggling to overcome the heat, like to design some heat isolation design. However, see, when I viewing the YouTube video, I suddenly noticed this project, the open source nano positioner for high precision analytical applications. It provides a very low cost nanometer levels positioner. So we can take a look. And yeah, this is his project. And the principle of this nano positioner is very simple. We got a PZT and so-called the piezoelectric material. When you apply a voltage, it can move back and forth. So we can take a detailed look on the right on this image, the graph B. Okay, so this is the PZT, so-called the piezoelectric material, and this is a magnet, and we got a linear slider here, and the piezo material, when you apply a voltage, it will deform. So in this case, when you apply a positive voltage, the PZT here, it will extend. And when the magnet is attached to the PZT, the magnet will move, like in this case, you will move to our right hand. You will move to our right hand side. And the linear slider here since the movement is very slow, so the linear slider will follow the movement. However, when we suddenly set the PZT or the piezo material voltage to 0, the PZT here will get a very quick reject. So the magnet will retract very fast. Due to the stick slip phenomenon, the linear slider won't follow up the movement of the magnet. So in this case, we generate, so a single sawtooth, we generate a delta S, and this is a single step. And with a multiple sawtooth, the slider can generate a continuous movement, like boop, 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 like moving to, in this case, it can move to our right hand with a continuous movement. So this is how so inspiring by this project, I use his piezo positioner into my project, and we can see the structure of my, this is my STM. And here is the scanner, so-called, and it is the piezo buzzer here, and just like dance design, just exactly the same one from here. Yeah, just exactly the same one. And we got a piezo slider and or low cost XYZ positioner here. And when the STM working, we can the sample can load it here, and the slider here can bring the tip and sample into the range of the scanner. After that, we can use our scanner to establish a tunneling current. So after that, we can just design our software to accomplish this procedure automatically. And this is the software. I program it with the Python and the Qt. Yeah. And that basically is all the content. Oh yeah, we need since the distance between the tip and sample is very close, so every tiny vibrations will cause a shake, so the tip may crash with the sample. And in this case, I designed a very simple damping system with 4 spring and with a stone, so it can generate just a hanging damping system. And in this case, we can generate a very low frequency, very low resonant frequency. And still, it's a very simple damping system. And when I get the atomic level image, I tried many times. Yeah. And so that's basically of my project. And if you are interested, you can search OpenSTM in GitHub or in open source hardware lab, or you can, in this case, you can get my paper here in docs, and this is my paper. And if you are interested, you can look into my description. So in today's live stream, we are going to focus on the PCB design. And maybe before we go in that, we have some gift for the audience, just you, and we can have some bonus time.
Yeah, today we prepared. Today we prepared 20 coupons from GLC PCB. Each was $50, and you can use them for PCB orders, PCBA, or even the colorful silk screen, whatever you like. We are going to play a little game called 3-2-1 Customer ID. Here's how it works. I'll count down 3, 2, 1, and when I say 1, everyone can send a message in the chat. Whoever appears at the very top of the chat list will win the coupon. It's that simple. So get ready. Don't miss your chance to win. 3. Good luck to all of you. 2. Maybe you say the last number.
1. Now you can send your customer ID to chat, and we will randomly pick one of you as our winner.
Oh.
Yeah, so we will so the lucky will be will be informed by our staff, and pay attention to our subsequent information. And thank you.
Congratulations.
And we will take a short break.
我加了滤镜，你看背景那个蓝色变成青色，
是蓝色。
有色差。
这里变色了吗？
So welcome back, and so this is the piece, and as I mentioned before, and all these PCB are designed using the EasyEDA, and we can take a look, and if you are like, this is the open source page, and if you click this open design drawing, and you can get into my my circuit design, and basically there are a lot of PCBs here.
Yeah.
And I can introduce it briefly. And for the control board, this is the control board, which is basically just this one, and as I can show you in front of the camera. Yeah. And this is the design, and we can get into the schematic. And basically it consists of 4 16 bits DAC, and this is 85761, and it is 16 bits DAC, and this is high accuracy voltage references, which provide voltage references to this DAC. And this is the first one, yeah, this is the second one, this third one, and yeah, there's total 4 DACs. And the circuit here is 2 sets, and basically 4 operational amplifier, and these 2, in this case I use OPA 2227 to generate the voltage which compatible with the buzzer scanner in this case. And this is a voltage follower, which just to amplify to increase the driven ability of the DAC. And this is 16 bits ADC, yeah, and ADS 86X85. And here is external 12-bit. Yes, this is a 12-bit DAC for the piezo slider driven, and this is also a voltage reference. Yeah. Yes. Yeah, it is voltage references. So this is a control board, and the MCU board. Since this project is started 2020, the MCU I used is ESP32. Yeah, very simple. But however, I didn't use the wireless function, and I just regard it as a simple MCU. So this is basically, the MCU board is basically like a development board, ESP32 development board. So yeah, this is the ESP32 module, and this is the USB to, and this is the USB the UART to USB strip. Yeah, this is very simple. And power board, which is we will introduce detailed in today's live stream. The power board is looking like this. It can, the input of this power board is 5 volt in our case, and just USB power, and we can see this is the power in, and this booster here is ADB 5070, and it can generate, it can convert the 5 volt voltage to positive and negative voltage, and then the positive and negative voltage will go through like a low noise LDO. In this case, I use the like ADB 711.8, and for the positive voltage, and ADB 711.8 is sorry, this is positive. Negative is ADB 71828 for the negative voltage, and I have prepared some image here, and this is captured by oscilloscope. The yellow one is the noise of our USB adapter, and in this case we can see a very high amplitude noise here, and the blue one is the output of our ADB 5070, and in which case is also very high level noise, and the purple one here is the output from our low noise LDO, and we can see the voltage, the noise level become very low, a very low noise level, and we can take a close look, and we can see typically the range of our output noise is around 4 millivolts. Yeah. So this power board provide a very low noise voltage supply. And maybe you are noticing that I'm using the EasyEDA with the web browser, which is very convenient. That's why I choose the EasyEDA. So in my scenario, I can launch EasyEDA with my web browser without downloading any client, and it's very convenient for me because I have multiple laptops, multiple PCs, and I don't want to spend some time to synchronize my project. So the EasyEDA provide a cloud server, and since I finish I finished my project in this computer, and I go to school with another computer, I didn't need to copy my project file. I just log in my account, and I can continue my project. I continue my PCB layout without downloading the client or the cloud server. And also, the useful function here is the version control and version management, and it's very similar to a Git control, because when you finish your you're drawing your PCB today, you have finished your work, and maybe tomorrow you have changed some details of the PCB. However, you find some mistakes, and you can go back to a previous version with the version control. And further, after you finish your PCB design, we can just click a simple click here, and we can order the PCB, order our component, or even further, we can ask a JLC PCB to solder in our PCB. Yeah, it's a very convenient function, I think. So, and that's one point I'm using the EasyEDA. So since you may notice, so let's take a quick view of the other PCB, the preamp. Yeah, the preamp just simply a TIA, and this is OPA 627. The reason I choose this chip because since the tunneling current, right? The tunneling current is in the range of nanoamps, even the picoamps. So we need a very small input bias current for our op amps. So that's after the balance between the cost and the performance, I chose OPA and 627, and it can work well. And the picture shows here just a simple TIA amplifier, and the feedback resistor is 100 mega ohms, and yeah, it can work. And we can take a look at our, yeah, this is the TIA board. Maybe we can click a 3D view for it. Yeah, here is our chip, and all the signal connection is via a FPC cable. And this is the connect board, just to connect the signal between the control board here, to sample and piezo sliders. Yeah, just a connect board to transfer the connection. And the sample table, and you may see some of the PCB, some of them are just act as a like structure component. Yeah, that's it. The PCB is I think it's a very solid material, and we can use it to act like a structure component. And this is we will like solder a magnet here, and so our sample can attach to it. And here is then maybe if I explain the details you will be confusing, so I just showing some design here. And the scanner connector just for the connecting. Just the quick. And this is the like a tip holder. Actually, we will solder a AMCX socket here, and then we can insert a tip into the AMCX socket. So let's maybe take a look at how can we draw the this power board here. Just this one. So the power board, just basically this is the booster circuit, and with the ADB 5070, the input the input here, input is 5 volt, and out is a I drew it a long time ago, so I need to spend some time to find a label. Here is input, and then the booster will boost the 5 volt voltage into, like, here is the positive, in this case is a positive 15 volts, and V negative in this case is a negative 15 volts. Then the positive and negative voltage will feed into the low noise LDO. Here they are totally 1, 2, 3, 4, 5. And so before we begin our drawing of the power board, the best way to learn something about this chip is to read its data sheet, right?
The components data sheet.
Yes, the data sheet. So the booster here, we can see the data sheet is from Analog Devices company, and is DC-DC switching regulator, which can generate positive and negative outputs. And this is the typical application circuit. And we can see some detailed information here. We can input, this chip can input range of the chip is 2.2 volts, 2.85 volts to 15 volts. And the output, it's adjustable. So, and we can scroll down to the specifications. We can see the input voltage range here, and this is what do you find the output? Oh, it's a fixed output. Sorry, it's a very long time ago for me to design this chip. We can see the positive 39 volts and the negative 39 volts. It's a very powerful booster. So let's continue. So this chip has two kind of package. The QFN one is currently I'm using. But if you think this one is difficult to solder, we can use the this one package, the TSSOP. I'm sorry, this is the LF6P package. This one is easier to solder, but depending on your project. And down here is the pin definition. We can see a lot of pins here. There are different functionality. We will go through the details. In today's we just directly go to the typical application circuit. And in here, in page 24, it provides a application circuit which perfectly fit our project, since the input is 5 volts and generate 17 volts and positive and negative voltage here, and then the voltage feed into the low noise LDO. In this case is the ADP 7142 and this ADP 7182 to generate the positive and negative low noise voltage. So maybe we can draw this schematic with EasyEDA. And just quick demonstrations, and we may not have enough time to cover the whole workflow, but we can demonstrate some function. We can demonstrate some function of our EasyEDA. Before we getting started, maybe we can have a bonus time.
Another giveaway.
Yes, another giveaway time. So you can send your customer ID to our. You can count 3, 2, 1.
Okay. 3. Are you ready? The lucky winner, I'll send you the coupon for your EasyEDA account. Each was $50. 2.
And welcome back. So let's continue our PCB drawing. So as mentioned before, we are going to reference this typical application circuit and online and choose the Pro Edition. So when the software, like if EasyEDA release some update, so you didn't need to like install the update on your own computer. You just open the browser and the update will automatically to you. So here we can click File New to create a new project. Let's say low noise power supply, and maybe you can add some description. And click Save. So wait a second for the project creation. So once you finish your project creation, we can get into, we can see it's created a board here, and we can double click to its schematic. You can change the profiles here, like the company and blah blah, and in this case I'm not going to change it. So the first step is to find a chip, and we can hold and press Shift and Control and press F to open our library, and we can just type in ADP 77500 to find a chip. And there are, as we mentioned before, there are two kind of package. What about we choose this one and click place. So we just place the component here directly, and we can just follow we just literally copy this to our schematic. Yeah, so that's we can hold it. So we just doing this step by step, and so if you're interested, you can download the datasheet ADP 5070 and turn to page 24, and you can see the schematic. So in our cases, we can I can put the schematic aside, and I can see both editor and application circuit. So if you're confusing what I'm doing, you can download the datasheet. So let's continue. The first, so when we replicate this schematic, I think maybe we can start it from the input, like here. And actually, there are some special requirements, like we can replicate the schematic first in this part. So the 5-volt input here, we have to place a C-in 1, and the C-in 1, there are recommended component with TMK blah blah blah. It's for tile Uden. So we can try to place this component to search whether, oh yeah, it's available. So you can place it and place it, like in this case is P V in 1, P in 2, P in system. Okay, these 3 pins. P in where is the P in 1?
Here.
Okay, P in 1. We can use shortcut key W to place a wire, and P in 2, and P. Okay, these 3 pins. They are all connected to this capacitor, and the capacitor is connected to the ground. Actually, there are some, if you are reading this, if you notice that there are different ground symbol. Like this one is like triangle. However, here is like three lines, and this indicates different ground plane. And for the triangle, which indicates the simulation, the analog ground plane. And for three lines here is for the digital ground plane. Am I right? Yeah. So since we're placing, we have to, although they are indicates the same, like a same net label, when you lay out your PCB, you have to isolate them. Like if you are like you don't want to design the PCB layout, you don't want to care about too much, you don't want to care too much about them. You can just follow this layout here, yeah, and you can like to achieve a good performance. So let's continue. And yeah, this is 3. We just copied it. So copy it. We can place in here is ground. Here is for the digital. Digital one. Connect to the ground. Okay. And for this one, we need a CC1. Is there any specifications? We can scroll down. Yeah, we can just use use a normal 12 kiloohms resistor. And we can find a resistor. And still 623 package with 12K ohms here. I think this one is okay. And put it here, and we need a 47 nanofarad capacitor. And capacitor. and 0603. Okay. 50 volts, and I think 50 volts is enough. Put it here, and it's connected to COMP1. COMP1 is here. Yeah, resistor. And we play a ground plane. It's AG and D. It's and I think there are, and COMP2 is 68 and 50 kilo ohms. Sorry, 68 nanofarad. 68, and we can clear our result in 68 nanofarad. Is 50 volts. Yeah, and 15 kilo ohms. Oops. We just Ctrl C, Ctrl V to copy our net flag. Okay. And this is the enable, and this is which indicates the high voltage level. High is on. So maybe we can connect it to where? How to set the default? I'm not 100% sure, but I think we can connect the enable to the input. Like we can, and this is only for the demonstrations. So you need to refer to the datasheet, like for clearly, and to find out the what actually these two pins need to connect it to. So for demonstration, I just connected the enable pins to the input voltage to enable the functionality. So we can place a net label here, input, and input here is okay. The SS pins, I think, is a soft start. We can, if you are not sure what's the functionality of the SS, we can go back to the pin function descriptions. It's a soft starting programming, and leave this pin open to fast it. Okay, we can leave it open, and also we can see that this is the boost regulation position enable, and it's compared to an internal position reference to enable. So we are going to not connect it. Maybe we can let me remind me to my previous design. It's power board. The enable here, and what we are going to connect. It can be set it to ground. It can float it. Actually, I think it can float it. We enable it from here. So you can literally copy my design. It can work. Yeah, I verify it. It can work. So let's continue. So we just leave it. It can be floated. So this 3 pin can be floated. And the next step, and the sync frequency, connect to flow, connect to the ground. Sync frequency here. And there are 6.8 inductor, micro inductor here, and we can see the 6.8. Is this as same as here? Maybe there are no special requirement, I think. Voltage in is here. We can with this inductor. And again, back to EasyEDA, we can search the, So this is very convenient. We do not need to like draw our package, draw our schematic symbol. And we need a DFL S240. Again, we just scan, we just search. Oh, no L, no L. Text 7. And there might be a little bit different between, like, with different suffix. So again, just demonstration, we just choose this one, and if you have any like requirement, you have to take a detailed look for this component. I just place it here to demonstration. It's connected to SW1 IP. Okay, SW1. So here to here. And this diode is positive 15 volts. Okay. and 2.43 mega ohms resistor, and these two resistors. Two point four three mega ohms. So it's very time consuming.
Yeah.
Yeah. To choose this. However, once you finish your design, like if your every designs in our library, you can just order you can just order all of your component at once. Maybe this is not available since it is a simple. Yeah, this is good. $137K. Yeah. Okay, this is from feedback. FB1 is so far away. FB1 ground. Here it's so you can optimize your routes. It's not very elegant way here. I drawing here. See out 10 microfarad. Two C out. Maybe we can set a very high voltage rating, like 50 volts. So this one. Two here. PG and D. This is 15 volts. We can place a net flag. SW2 here. W2, and you can notice the difference of the negative voltages. The diode is reversed. This is the negative. Okay. So again, we need to set the resistors. 118. 118. Okay, I think it's time to have our bonus time, and we are going to give away the gift.
This is the last opportunity to get the coupon. Okay, don't miss the chance. You must have. So many people. 1. Okay. I have said 1.
So you can send your custom ID, and we are having the bonus time. So our staff will randomly pick, and we will have a short break, and after that we will continue our schematic.
See you later.
So let's continue our schematic drawing. So let's back to the schematic, and we need to I can simply copy and paste. There might no symbol available here, but I think we can choose from our the common library and set the resistance to okay. So when we buying this, and then we can, and since it is not contain the details of manufacturer, we have to choose it manually. Yeah. Okay, B2. Between them. And we need an extra ground capacitor. See, is this one for Murata. Okay. Oh, we need actually this inductor. Okay, we can place this one to ground. SW2 to ground. SW2 to ground. Oh, this is ground. anything I missed? Oh, here. VREG. Which pin? VREG. Here.
How connected?
It's connected to the ground. This. Okay, and the AG and D, it's where's AG and D? Oh, it's select the symbol, just connect it to here. Oh wow, now we have finished our, okay, SEQ, SLEW, we can flow. So it can be floating. So now we have finished our booster design. For the LDO, we can demonstrate the positive one. Okay. 7-1. Okay, this is the data sheet, and we can. It's really simple, however. ADP 7142. And here we go. So there are some special requirements for the capacitor, and we can scroll down. And which requires like a polarized capacitor here. And here we go. We can see the voltage formula here, so we can change the resistor here to achieve different voltage output. However, this is what we required. It's 12 volt settings. Just copy it. Here it's a 2.2 microfarad polarized. And we can choose the category. Is this type of polarized? So let me double check the capacitor type.
Friend, tap 啊，难怪。
Maybe we can just use this manufacturer. Okay, we can use this, just this one, because yeah, this type of capacitor. And 1 microfarad. I think this is not strictly necessary. Go back to the top. Okay. Yeah, it's not strictly necessary. See in, see out. And what about we just put 2K and 10K here? We can. This is SW1 is positive or negative? Oh, it's positive. Okay. And be in here directly to our LDO. Soft start is a 1 nanofarad. Ground. The enable pin can be, which I think it can be just directly connected to the VIN, and the EP can be, I think, connected to the ground. And be out, we can place another. Yeah. Here. Where the output is, when we follow this schematic, the output should be 6 volts. We need a 10K and a 2K resistor. It's 2K. Okay. We out to ADJ, it's 2K. Out to ADJ, and this is to ground. Okay, that's we are roughly finish our like low noise circuit design, and it's not cover every detail, so there may contain some little mistake. And if you are interested in to draw like no noise power board, you can refer to the datasheet of ADP 5070, and in page 24 there are very typical application circuit. Here you can refer to this circuit, or you can refer to my this power board. You can just since it's open source, you can just copy and paste my schematic, even the PCB layout, and it's free and it's okay for your project, and that's the design of the power board. And if you want to design your own one, since we have already finished the schematic layout, we can convert it to the PCB. Yeah, once you're converted to PCB, you can refer to the ADP's 5070 datasheet for its layout, and there's a very detailed layout here, and the LDO's datasheet layout, and all the layout you can find in his datasheet, and you can refer to the like how the ground plane goes and etc. from here. Yeah, so that's basically cover the whole things of today's live stream. And if you are interested in my project, you can search OpenSTM, the keywords on Open Source Hardware Lab, or GitHub, or search my social media ID, Deems Mary, on YouTube to watch my video. And yeah, before we end it, we have some times, like 6 minutes. You can ask any questions you want, you would like to know to the chat, and we will have very last round giveaway time when since we maybe 5 maybe 30 6 minutes later, we will have another very last round on this live stream. So you can feel free to chat and to ask, feel free to send chat to ask any questions, and I will answer you.
Have you ready your customer ID? Okay, let's begin. It's the last opportunity to get coupon from GLC PCB, $50. 3. Don't miss the chance. The last 5 winner lucky one. 2. Are you ready? 1. I have said 1.
Okay, thank you. Hope your project going well.
You said too much. I'll see you.
Yeah, thank you.
Thank you.
Our staff will randomly pick pick one of you or some of you to give away our coupon.
I'll send the coupon to your EasyEDA account. If you have any question, you could send email to selena@easyeeda.com.
Thank you, the amazing secretary. Thank you. Thank you, Digital Toaster. Thank you, thank you.
하와이吧，还是
Okay, sequel. See you.
Thank you all so much for joining today's live stream. We hope you enjoyed Waring's amazing OpenSTM project and learned something new along the way. If you like this kind of deep dive engineering content, don't forget to follow our channel so you won't miss future live shows, tutorials, and engineering demo. Have a wonderful day, stay creative, and we'll see you next time here at EasyEDA Live.
So,